All right, so we're going to go through an example of how we can find the upper and lower sums for a function. In this case, we're going to look at the function f of x equals x squared from 0 to 2. So let's first draw a sketch of what's going on here. So we know, or we should know, that this is very popular quadratic function, parabola doing this sort of thing. Y equals x squared from 0 to 0, so to 2. Now, since this is a strictly increasing function, since it's, since it's always going up, or since the values are always getting larger as you move from left to right, if we draw, let's look at a couple of rectangles, what would happen? We draw rectangles with right endpoints, so right endpoints on the graph of the function. You can see that this would overestimate or over approximate the true area. So this will be an upper sum, because these rectangles are, going above the area of the region. The area of the region is only right here. So using right endpoints, this would give us an upper sum. So let's first calculate this one. So the upper sum, let's find a way to represent the value of the heights and the widths of each rectangle. So the width or delta x of each rectangle will be, remember, the total width of the interval, b minus a over n. B is 2, a is 0, so it's just 2 minus 0 over n, or just 2 over n. So each rectangle will have a width of 2 over n. The heights of each rectangle, let's get an idea of how this would work. This would be, let's say that would be x1, this would be x0, this would be x2. So f of x1, f of x2, f of x3, and f of x4, f of x all the way to f of xn. So what we want to look for are values, how we can get the right endpoint. If we make I equal to 1, 2, 3, 4, 5, all the way to n, then the right endpoint will just be 2 over n times I. So for I equals 1, 2, 3, 4, 5, all the way to n. And a general formula you can use, if you need one, is just a plus I times delta x. So in this case, it would just be 0 plus I times 2 over n. So 2I over n. So going back, kind of out of order here, the heights of each of the rectangles would then be f of 2I over n. And so then we can write upper sum, and we're going to use large S of n, I mean, will be equal to the sum from I equals 1 to n of f of 2I over n times 2 over n. Remember, the height times the width. Height times the width. Working this out from I equals 1 to n. The function is, remember, x squared. So what we're going to have here is we're going to put 2I over n in for x. So we're going to have two I over n all to the second power times 2 over n. And I don't like, let me write this a little neater. I don't like the way that's looking. Okay, and then we got to work this out. So what would happen here is we're going to get the sum from I equals 1 to n, 2I squared. That'll be 4I squared times 2. So what we're going to have is 8I squared over n squared times n, because it's n squared times n, so over n cubed. We can factor out, or think of it as factoring out, the 8 over n cubed outside the series. So 8 over n cubed times the sum from I equals 1 to n of I squared. And then we can use a formula to rewrite and simplify I squared. This will be equal to 8 over n cubed times the sum from I equals 1 to n of n. Actually, we don't even need this anymore. Times n times n plus 1, 2n plus 1, all over 6. And then we just break this down. So let's see what we can get here. So we'll have 8n times 2n squared plus n plus 2n, so plus 8n plus 2n squared plus n plus 2n, so plus 3n plus 1 over 6n cubed. Multiplying each of these by 8n, it's 16n cubed plus 24n squared plus 8n over 6n cubed. And then let's see if we can so we can factor out. So we can power everything down. We can put this as 16n cubed over n cubed. Those n cubes will cancel. So let me rewrite this like this. Let's rewrite this as 16n cubed over 6n cubed plus 24n squared over 6n cubed plus 8n over 6n cubed. So these n cubes will cancel. This will become 8/3. And that'll just power down to an n, 24 over 6, that'll just be 4 over n. And then that n will go away, that'll just be n squared, 8 over 6, 4 over 3n squared. Okay, so now we have a general expression if we want to calculate the sum of n rectangles for right-hand points, so an upper sum. We're going to go back and I'm going to just talk more about what this means after we find let's find the lower sum now. The lower sum is just going to use the left endpoints. So draw another sketch down here so we can get a clear idea of what exactly we're talking about here. Same sort of thing, except we're using left endpoints. So like it would be something like this. Let's say we're going from, again, 0 to 2. Pretend those are the same width, but your rectangles would be like these guys right here. So that would be x0, this would be x1, x2, and so forth. This would be xn. Okay, so we're going to use left endpoints. So it's going to be a little bit of an adjustment from this one. So lower sum. The width will still be the same. The width will still be delta x, which is 2 over n. Because the total interval is still 2, so the width will still be 2 over n, and that again is just your delta x. Now your left endpoints, though, we can do a simple formula expression that you can use for that is just going to be a plus I minus 1 times delta x, if you need some help. In this case, a is 0, so it'll just be 0 plus I minus 1 times delta x. Delta x is 2 over n, so this times 2 over n. Those will be 2i minus 2 over n. Okay, so then your lower sum, so little s of n, will be the sum from I equals 1 to n of f of 2i minus 2 over n. This will be your height. These will be your heights. Times delta x times your width, which will be 2 over n still. And remember, since our function is x squared, we're going to square this. we're gonna have 2i minus 2 over n squared. Okay, so let's go to this line. So we're gonna have sum from I equals 1 to n. Squaring this, we'll get 4i squared minus 4i minus 4i plus 4. So this will be 4i squared minus 8i plus 4 over n squared, because we're squaring that bottom part too, times 2 over n and try to squeeze it in here if I can. Let's see if I can fit it on this page. So from I equals 1 to n, distributing that 2 to each of those, 8i squared minus 16i plus 8 all over n cubed. So far, so good. And then let's see if I can do one more line. Okay, so here we can factor out an 8 from each of these and an n cubed from the denominator. So this will be 8 over n cubed times the sum from I equals 1 to n of I squared minus 2i plus 1. Now here we're gonna break this up into three sums. So we're gonna have 8 over n cubed multiplied by the sum from I equals 1 to n of I squared plus the sum from I equals 1 to n of negative 2i. And actually I could just carry that negative out here. It'll probably be easier. So minus 2i plus the sum from I equals 1 to n of 1. Now I'm gonna have to go on to the next page. But from here now we can use formulas to simplify each of these. Each of these are just formulas that I went over in the first part of this lesson. So this will be equal to 8 over n cubed times, for I squared, you'll get n times n plus 1 times 2n plus 1 over 6 minus 2n times n plus 1 over 2 plus n. These twos will cancel. If I want to combine all these, I can put them all over 6, I believe. Let's see what we get. So 8n cubed plus 3n plus 1 minus so that n squared, and I'm going to multiply them also by 6. So 6n squared plus 6n over 6 plus 6n over 6. Just so I can combine all the terms together. Oh, whoops, and this is all over 6. And multiply everything by n cubed here as well. And the 8 on top. So this will be 2n. Let me actually go slowly because this will be, I want to make a mistake. 2n cubed minus 3n plus n over 6 minus 6n squared plus plus 3n squared minus 3n. So plus 3n squared minus 6n, so minus 3n squared plus n minus 6n, so minus 5. These cancel out, plus minus 6n plus 6n, so this will just be plus n here. All over 6, multiplying across by 8. 16n cubed minus 24n squared plus 8n all over 6n cubed. And then going step by step, not if you need me to, here, that's what I'm here for. 16n cubed over 6n cubed minus 24n squared over 6n cubed plus 8n over 6n cubed. These n cubes will cancel. 16 over 6, that becomes just 8 over 3. The n just becomes just an n, that just becomes a 4 over n. That just becomes an n squared, so 4 over 3n squared. So this is the lower sum. So the upper sum found to be pretty similar. It's 8/3 plus 4n plus 4 over 3n squared. The lower sum, that 8/3 is still there, except you're minusing that and then adding that part. Now, the idea is this. If you take the limit as n goes to infinity of each of these sums, the limit of the lower sum, so lower sum, you took the limit as n goes to infinity, this essentially would go to 0, this would go to 0, and it's essentially 8/3. Let me just write s sub n to be a little more formal. Small s sub n would just be 8/3 minus 0 minus 0, so it would just be 8/3. And the upper sum, large s of n, taking the limit of this also goes to 0. That goes to 0, that goes to 0. So it's just 8/3 plus 0 plus 0. And you're going to find that they both equal 8/3. And that's the beauty of this math and what we're going to go over in detail about the integral is that we can find that if you go and create an expression that essentially is approaching an infinite number of rectangles, you're going to find that it doesn't matter if you're using left endpoints or right endpoints, the rectangles are gonna get so infinitely like thin. I don't like this check mark actually. So infinitely thin that it doesn't matter which one you use. It's gonna be accurate either way. And so we're gonna go into that in the next couple of lessons.